Maths class. I am Julia Alalibo. Today we'll be studying the theme Numbers and Numeration, and the topic is Whole Numbers Part 2. We've looked at Part 1 of Whole Numbers, where we talked about the various number systems, especially base 10. And for today, our content is binary numbers, converting from other base system to binary system and vice versa. And thirdly, operations with binary numbers. So by the end of the lesson, I expect that you should understand binary numbers and solve simple questions on binary numbers. Now, the binary or base 2 number system is based on the number 2. Remember, the denary system or base 10 system is based on the number 10. But for the binary or base 2 number system, it is based on the number 2. The binary number system consists of two numbers only. They are 0 and 1. An example is 11001100. This is actually a number in base 2. A bit is a single binary digit. Now, these are 8 binary digits. One of these digits, say this one, is called a bit, a single binary digit. And it is gotten from the B in binary and the IT in digits. So one number here is called a bit. Now, a sequence of 8 bits make a byte. If you have 8 bits, 8 binary numbers, like this example which we have here, 11001100. These are 1, 2, 3, 4, 5, 6, 7, 8. So this is actually a byte. A sequence of 8 bits make a byte. Now you might be wondering, why are we looking at binary numbers or base 2 numbers when we have other ones apart from base 10? Why not look at base 3 or base 4? The importance or application of binary numbers. Binary numbers are very important because they are used in the computing world. For instance, the switch in an electronic circuit has only 2 options. When the switch is on, it is read as 1. And when the switch is off, it is read as 0. So most of our computers and our gadgets, the only language that they understand is the binary number or the binary language. Another importance of the binary number system is that computers can only communicate in binary. And the third importance is any character you type on your keyboard is interpreted by your computer as a byte, an 8-digit binary number. So computers make use of binary number. When you use your keyboard to make an input, it processes it as a binary number made up of ones and zeros. So the knowledge of binary numbers is important for computer applications. The first example which we have here is convert 5410 to binary number. This is 5410, and to convert it, we are asked to convert it to base 2 or the binary number. And from part 1 of this lesson, we learned that when converting from base 10 to any other base, even if it's base 2, that is the binary number which we're talking about, we do that by the method of repeated division. We divide until we get to 0. So this is 54, and converting it to base 2. Base 2 is the desired base. So this is our remainder column. So 54 divided by 2 is 27. The remainder is 0. 27 divided by 2 is 13. The remainder is 1. 13 divided by 2 is 6. The remainder is 1. 6 divided by 2 is 3. The remainder is 0. And 3 divided by 2 is 1. The remainder is 1. 1 divided by 2 is 0. The remainder is 1. So this in binary numbers, as per usual, we take from the bottom to the top. So this is 1, 1, 0, 1, 1, 0 in base 2, which is what we have here. So 5410 is equal to 110110. Now, example 2, convert 2658 to binary numbers. Now, we only talked about converting from base 10 to another base or from another base to base 10. Now, here we are asked to convert from base 8 to binary numbers or to base 2. Now, to convert from 265 to base 2, We don't go straight. There's no way of converting directly from 2658 to base 2. So the first step is to convert 2658 to base 10. So we are going to use the method of expansion. You know, there are two methods of converting to base 10, either expansion or repeated multiplication. But we are going to be using the method of expansion. So we have 0 here, we have 1 here, and then we have 2 here. And the base is base 8. So we simply multiply 2 by 8 raised to the power 2, which is what we have here. 2 times 8 raised to the power 2. And then 6 times 8 raised to the power 1 plus 5 times 8 raised to the power 0. So we can expand this. We have 2 times 8 is 64 plus 8 raised to the power 1 is 8, 6 times 8. And 8 raised to the power 0 is 1. Any number raised to the power of 0 is 1. So we have 2 times 6 gives 128, 6 times 8 gives 48, and 5 times 1 gives 5. So 128 plus 48 plus 5 is equal to 181/10. So we've succeeded in converting 265 8 to base 10. So this is actually equal to this. 265 8 is equal to 181/10. Now it will be easier to convert 181/10 to base 2. So we simply convert 181/10 to base 2. And we do that by the method of division. So we have 181 divided by 2. This gives 90 remainder 1. 90 divided by 2 gives 45 remainder 0. 45 divided by 2 gives 22 remainder 1. 22 divided by 2 gives 11 remainder 0. 11 divided by 2 gives 5 remainder 1. And 5 divided by 2 gives 2 remainder 1. 2 divided by 2 gives 1 remainder 0. And finally, 1 divided by 2 gives 0 remainder 1. And our answer is the remainder from the bottom to the top. So we have 1, 0, 1, 1, 0, 1, 0, 1, 2. So to convert 2658 to binary number, it is equal to 1011 01012. Remember, when asked to convert from a base to another base that is not 10, we first convert the number to base 10, then convert it to the required base. Example 2, find 1102 squared in base 2. Now we are asked to convert the number, or we are asked to find the square of 1102 in base 2. What do? We first of all, we convert 110 or 110 to base 10. And we do that by the method of expansion. So we have 0, we have 1, and we have 2. So we have 1 times 2 raised to the power 2, which is what we have here. 1 times 2 raised to the power 1, which is what we have here. And 0 times 2 raised to the power 0, which is what we have here. On expansion, or on doing the addition here, the multiplication and addition, 2 times 2 is 4. 4 times 1 gives 4. 2 times 1 is 2. And 0 times 1 is 0. So 4 plus 2 plus 0 is equal to 610. So we have succeeded in converting 110 to base 10. The next step is we have to find the square of 1110. So since 1110 is equal to 610, if we have to find the square of this, we can simply also square this. So the next step is square the number in base 10. 1110 squared is equal to 6 squared. And 6 squared, which we know is 6 times 6, is equal to 3610. This is the square of 1110. But now we have to convert it back to base 2, because we are asked to leave the answer in base 2 and not base 10. So converting 36 to base 2. Again, we do our long division, method of repeated division. 36 divided by 2 gives 18, remainder 0. 18 divided by 2 gives 9, remainder 0. 9 divided by 2 gives 4, remainder 1. And 4 divided by 2 gives 2, remainder 0. 2 divided by 2 gives 1, remainder 0, and 1 divided by 2 gives 0, remainder 1. So the answer is the remainders from the bottom to the top. That is 1, 0, 0, 1, 0, 0, 2. So the square of 1102 is 100, 1002. Example, find the square root of 110012. As usual, we first convert to base 10, find the square root of the answer gotten in base 10, and convert back to base 2. So to convert this, we do this by method of expansion. We have 0, 1, 2, 3, and 4. So we have 1 times 2 raised to the power 4, 1 times 2 raised to the power 3, 0 times 2 raised to the power 2, 0 times 2 raised to the power 1, and finally 1 times 2 raised to the power 0. Now 2 times 2 times 2 times 2 is 16. 2 times 2 times 2 is 8, and 8 times 1 is 8. Here, 2 times 2 is 4, but 4 times 0 is 0. Here, 2 times 0 is 0. And here we have 2 raised to the power 0 is 1. So 1 times 1 is actually equal to 1. So we do the addition, we add up. 16 plus 8 plus 1 is 25. So 110012 is equal to 2510. And we are asked to find the square root of 11001. The next step is to find the square root of the number in base 10. So square root of 11012 is equal to the square root of 2510. Square root of 25 is 5. This is equal to 5. The square root of 110012 is 510. But we want the number in base 2. So we convert 5 to base 2. So we have 5 here. 5 divided by 2 gives 2, remainder 1. 2 divided by 2 gives 1, remainder 0. And 1 divided by 2 gives 0, remainder 1. So we write the answer from the bottom to the top, which is 1012. So the square root of 11001 is 10012. Now, let's look at some operations with binary numbers. Mathematical operations such as addition, subtraction, and multiplication can be carried out directly with binary numbers with the aid of the following identities. Now, in the previous examples, when we are asked to multiply or square a number in binary form, we had to convert to base 10 before squaring that number in base 10 and then taking it back to the base 2 form. We can do that directly if we know these identities. So for addition, 0 plus 0 is 0 in the binary form. 0 plus 1 is 1. But 1 plus 1 is equal to 10 in binary. We can explain this. Now, if 1 and 1 are in base 10, we have 1 plus 1. In base 10, it is actually equal to 2, right? So now converting this 2 to base 2, this number 2, this is actually 210 in base 10. If you convert this to base 2, let's convert it to base 2 and see what we get. So we have 2 divided by 2, and this is a remainder column. So 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. From the bottom to the top, we have 10, 2, 1, 0, 2. So we can see that 2, 10 is actually equal to 10, 2, right? That is why 1 plus 1 as an additional identity in the binary form is equal to 1, 0. Now for multiplication, 0 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. Let's look at a few examples to understand operations with binary number using their identities. Now, this example, we have 1011 plus 1001. So, I'm going to solve it out here. Now, 1 plus 1. Remember our identity for binary. 1 plus 1 is 10, not 2. So we write down as 0. As per arithmetic maths, we write down as 0 and carry the 1. 1 plus 1 is 10. Write down the 0 carry the 1. We have 1 plus 0 is 1. And then 1 plus 1 here is 1, 0. So 1, 0, 1, 1 plus 1, 0, 0, 1 is 1, 0, 1, 0, 0, 2 in base 2. So this is the answer for the addition of these based on the binary identities. Now for example 2, we have 1, 1, 1, 1 plus 1, 1, 0, 1 plus 1, 0, 1. Add up the 3. So we have 1 plus 1 plus 1. Now there's no identity for 1 plus 1 plus 1, but we know that 1 plus 1 is equal to 1, 0, right? We've added both of these. Now we can add 1 to this. So 1, 0 plus the remaining 1 which we have here. So 0 plus 1 is 1, and 1 plus nothing is 1. So it's 1, 1. We write down 1 and then carry the other 1 up. So 1 plus 1 here is 1 plus 1. From identity, we know that this is 1, 0. So we write down the 0 and carry over the 1. Now here we have 1 plus 1 plus 1 plus 1. So let's expand this. We have 1 plus 1 plus 1 plus 1. Now 1 plus 1, we know that this gives us 1, 0. Plus the next 1 plus 1, this also gives 1, 0. Now we can add this up directly. That is 1, 0 plus 1, 0. This is 0. And 1 plus 1 here, that is this 1 plus this 1, is 1, 0. That is, this is 100. 1, 0, 0. So what we have here is 0. We write down just this 0 and then carry over the remaining 2. Carry over this 1, 0 here. 1, 0. Now we have 1, 0 plus 1 plus 1. We expand that again so that we can solve this easily. So we have 1, 0 plus 1 plus 1 here, our binary identity. This is 1, 0. So we know that 1, 0 plus 1, 0, which we have solved here, gives 1, 0, 0. So we simply write it out here, 1, 0, 0. So the addition of 1, 1, 1 plus 1, 1, 0, 1 plus 1, 0, 1 gives 1, 0, 0, 0, 0, 1 with the aid of the binary identities. The third example on operations with binary numbers. We have 1, 1, 1, 0 minus 1, 0, 0, 1. Now, 0 minus 1, this cannot go. So we borrow from this one, arithmetic mass. So this becomes 0, and this becomes 1 here. So this is 1, 0. 1, 0 minus 1. Remember that 1 plus 1 is 1, 0. So 1, 0 minus 1 will be equal to 1 from this identity. 1, 0 minus 1 is equal to 1 if 1 plus 1 is equal to 1, 0. So this is 1 here. And this has become 0 because we borrowed the 1 from here to this point. So 0 minus 0 is 0. And 1 minus 0 here is 1. 1 minus 1 is 0. So this is equal to 1, 0, 1, which is what we have here as the answer to 1, 1, 1, 0 minus 1, 0, 0, 1. Now the fourth example, we have 1, 0, 0, 1 times 1, 0, 1. The multiplication identity, 1 times 1, 1, 1 times 0, 0, 1 times 0, 0, and 1 times 1 is 1. 0 times 1, 0, and all the way 0, 0, 0. So then multiplying 1 by this again, which is similar to what we did previously. So we have 1, 0, 0, 1. And then we do the addition. 1 plus nothing is 1. 0 plus 0 here is 0. 0 plus 0 plus 1 is 1. 1 plus 0 plus 0 is 1. 0 plus 0 is 0, and 1. So the answer to this is 1, 0, 1, 1, 0, 1. So this brings us to the end of our lesson for today. And we looked at binary numbers. We said the binary or base 2 number system is based on the number 2. It is the second most important base system because of its wide application, mostly in computing. We also looked at the operations with binary numbers and their identities. Now, before we go, we are going to do a few test questions. You can solve this and then come back later to check the answer. The first question is find the square of 24 5 in base 2. Now, this is 24 5. We said that whenever we are to convert from one base that is not 10 to another base, it's not quite simple. So what we do is we first of all convert this to base 10. So we have 0 and we have 1 here. So this is 2 times the base 5 raised to the power 1 plus 4 times 5 raised to the power 0. And 2 times 5 is 10 plus 4 times 5 raised to the power 0 is 1. So this is 14. 14, 10. We are asked to find the square. So we find the square of 14, 10, which is equal to 14 times 14. And this is equal to 196, 10. So this is the square of 24, 5. But then we have to convert this to base 2 because we want the answer in base 2. So converting to base 2, we have 196. These are remainder columns. So 196 divided by 2 gives 98, remainder 0. 98 divided by 2 gives 49, remainder 0. 49 divided by 2 gives 24, remainder 1. 24 divided by 2 gives 12, remainder 0. 12 divided by 2 gives 6, remainder 0. And 6 divided by 2 gives 3, remainder 0. 3 divided by 2 gives 1, remainder 1. And 1 divided by 2 gives 0, remainder 1. So this is where we stop since we have arrived at 0. So the answer is the remainders from the bottom to the top. So the square of 24, 5 in base 2 is equal to 1, 1, 0, 0, 0, 1, 0, 0, 2. And that is option C. So option C is the correct answer. Test question 2. We have 112 times bracket open 1002 plus 10102 minus 11002. So we are going to solve this using board mass. Board mass says bracket first. So we solve the bracket first. But in the bracket, we have addition and subtraction. And the first amongst both is the addition. So let's do the addition first. 1001 plus 1010. So we have 1001 plus 1010. Now, using our identities, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, and 1 plus 1 is 1, 0, not 2. Minus 1100, so 1100. So 1 minus 0 is 1, 1 minus 0 is 1, 0 minus 1, this cannot go. We can also borrow from this number because this is 0. So we come all the way here to borrow from this. So this becomes 0, and now this becomes 10. Now we also, since this is now 10, we can now borrow from this to give to this number. So if we remove 1, remember our binary identities, 1 plus 1 is equal to 10. That means 10 minus 1 is equal to 1. So if we remove 1 from this, what's going to be left is 1, not 9. So we have 1 here. So this is 10 minus 1. Our identity is 10 minus 1 is 1. And here, remember, we are left with just 1. 1 minus 1 is 0. And this is 0. So this bracket gives 1, 1, 1. Now multiplying what we got here by this. So we have 1, 1, 1 times 1, 1, 1. So 1 times 1, 1, 1, we have 1, 1, 1. 1 times this, 1, 1, 1. And 1 times this here, we have 1, 1, 1. And then we add up. This is 1. Binary identities, 1 plus 1 is equal to 1, 0. So 1 plus 1 here is 1, 0. We write down 0 and carry over the 1. So this is 1 plus 1 plus 1 plus 1. So we expand to have 1, 0 plus 1, 0. And 1 0 plus 1 0 is 0 plus 0 0. 1 plus 1 again is 1 0. So this is equal to 1 0 0. So 1 plus 1 plus 1 plus 1 is equal to this. So we write down this and carry over what's left. Now we have 1 0 plus 1, which is the same thing as this. It is also equal to 1 0 0. So we write down the 0 and carry over what's left. That is 1 0. So 1 0 plus 1. This gives 1 and 1. So this is and then this is the answer 1 1 0 0 0 1 2 in base 2. So the correct option is option D. If you chose D, you are correct. This brings us to the end of our lesson on whole numbers part 2, where we learned on the operation and application of binary numbers. Do have yourself a wonderful time.